Welcome to the chapter on the drainage function of geosynthetics. The drainage function is defined as collecting and transporting of precipitation, groundwater and/or other fluids in the plane or within the thickness of a geosynthetic material. Too much water in the wrong place is a problem in the world of ground engineering. If water isn't taken away fast enough, it accumulates or flows over soil, causing erosion. Then the silt blocks up the drains and the flooding gets worse. When water flows down a slope, it can cause instability in the surface or even lead to a deep-seated slip where a whole embankment comes down. Carl Terzaghi, one of the fathers of modern soil mechanics, said, "In engineering practices, difficulties through soils are almost exclusively not due to soils themselves, but to water contained in the voids." On a planet without any water, there would have been no need for soil mechanics. Once the water gets into the soil, it changes its nature and becomes unstable. So what is the solution? More strategically placed, effective drains? The traditional solution is to intercept the runoff water from either the infrastructure element, in this case a road, or the surrounding area, in this case an embankment. Typically, a trench filled with stone with a pipe near to its base is used, commonly called a French drain. Often it is desirable to drain a site before the main site activity starts to enable trafficking during the construction phase. The difficulty is getting the stone across the wet, muddy site to start draining it. Which is easier, moving 30 tons of gravel across a site or 32 kilograms of drainage geocomposite? And what is more, which will have a lower carbon footprint, but are the equivalent in their drainage capacity? Geocomposite drains are made up of a geotextile filter on one or two sides of a central spacer or core. Even in a coarse aggregate, the permeability of stone is slow compared to the geocomposite drain because of the water paths. The water path through the stone drain is irregular and random, whereas the flow in the drainage composite is direct and steady, in fact up to 1,000 times faster. This means 500 millimeters thickness of drain stone is equivalent to a 10 millimeter geocomposite. Highways England recognise the benefits of geocomposite drains, and you will find it referenced in the standard for highways works. The example shown here is the Type 6 fin drain, which contains an integral pipe. To place the fin drain, the width of the trench is dictated by the width of the pipe or minimum size of trenching bucket. You can even backfill with the soil you took out, saving cartaway costs. We have spoken about draining free-flowing excess water from the surface or within a soil. Engineers are often asked to use local soils to form embankments. These soils often contain large amounts of water which are not free-flowing and has to be drained out or squeezed out to make the soil stable enough to take, say, a motorway on top of it. Often at the beginning of a large project, suitable but wet soils are heaped into large mounds so that their self-weight will squeeze the water out of the voids in the soil, making it denser and more stable. The embankment also puts loads on the underlying soils, which also need to be drained as consolidation takes place. A common way to speed this up is to use a starter layer at the base. This is usually achieved with a layer of stone. A case study might help. Here is a site in Yorkshire where water tables are high and some high embankments were needed to create a smooth level highway. Stone starter layers were specified as the local soils tended to be fairly saturated. The problem was standing water on the cut formation and the difficulty of getting big stone lorries on and off the site over the whole of the base of the embankment. The contractor put forward an alternative geocomposite drain which could be hand carried onto the site and rolled out. As you can see from the diagram, it also saved 300 millimeters of extra excavation down into the waterlogged site. Whilst the starter layer takes away the water from the base, you still have to wait for the rest of the embankment to consolidate under its own weight. The problem is, this often takes a long time, maybe up to 2 years on some projects. The water between the particles, once again, caused the problem because the voids are so small. This often means the whole site program is dictated by the earthworks consolidation rate. By putting intermediate layers of geocomposite drain into the embankment, this will accelerate the process considerably. Intermediate stone drainage blankets are rarely used as they are so impractical. Again, a case study will help us to explain. After the M60 motorway around Manchester was built, there was a large amount of saturated soil which was to be used to make a large development site near the motorway. The owners wanted to open this shortly after the motorway was completed to catch the passing trade. The soil was formed into a series of cells with side slopes, including layers of geocomposite drain at regular intervals, which quickly drained into the next cell before it was filled, thus progressing across the site cell by cell. By the time they had filled the last cell, the other cells were consolidated, ready for construction of the buildings, allowing them to open on time. The consolidation period was 75% less than the just using a starter layer. Any buried structure is likely to be subject to groundwater pressures from one side. Retaining walls, culverts, basements, underground water reservoirs. Typically, the water table is lowered to the base of the structure and drained or pumped away, leaving it dry. This is often achieved using porous, hollow concrete drainage blocks stacked against the side of the wall, which are then filled with drainage gravel. How easy is it to install blocks and gravel behind a bridge abutment? What are the monetary and carbon costs to the project? Reducing the amount of traffic to and from site is a key source of carbon reduction, not to mention the damage and disruption on the roads to and from the supply site. To give you an idea, 40 truckloads of concrete blocks followed by 20 truckloads of infill gravel equals 1 truckload of geocomposite. A case study might again illustrate the benefits to a big site. The A14 Huntingdon to Cambridge Improvement Scheme was a £1.5 billion project and the largest highway project in the UK in recent times. Key issues for the site were drainage and environmental impact. The site took environmental protection seriously enough to appoint an Environment and Sustainability Director to look for ways to amongst other things, save carbon wherever possible. The project involved widening of the carriageway in sections, large new junctions, 67 new bridges and a 750-metre long viaduct which formed the new A14 road. Most of the structures on the site had buried elements to them and all needed draining. The contractor made their own assessment of the switch from concrete blocks to a geocomposite drain. 84% quicker to build. No site machinery needed. 80% saving on purchase and installation costs. And the best of all, 94% saving on carbon footprint impact. We've looked at dealing with flowing surface and groundwater, dewatering of saturated soils, and removing water pressure from buried structure. Some of the other applications which may interest you are mentioned above. Further guidance on the design and execution of geosynthetic drainage solutions is as shown in the list above. Another great source of information on all geosynthetic applications is to be found by joining the UK chapter of the International Geosynthetic Society with a dynamic student membership, which is also free for students in the UK. Joining also gains you access to leading geotechnical journals and conference proceedings, and even the chance to put papers and academic research into upcoming geotextile conferences around the world.